Geek Wisdom.
Disclaimer: the views and opinions expressed in this article are those of the authors and do not necessarily reflect the views of the employer. Examples of analysis and code used in this presentation are only examples. They should not be utilized in the real world products. They should be considered as based on limited and possibly dated open source information. Assumptions made within this presentation are not reflective of the position of the private or government entity to which the author is presently employed.
No man is an island, entire of itself. Every man is a piece of the continent, a part of the main. If a clod be washed away by the sea, Europe is the less. As well as if a promontory were, as well as if a manor of thy friends, or of thine own were. Any man's death diminishes me, because I am involved in mankind, and therefore never send to know for whom the bell tolls. It tolls for thee. In the early 17th century, English poet John Donne created this poem, and his words were very profound, because as humans, we all sort of compete for scarce resources. But at the same time, it's necessary for us all to work together towards a common good in order to survive. At the time that he wrote the poem, I don't think he knew anything about software components. That what's true of humankind is also true about the things that humans create. Recall that in part 1 we talked about the principles of good components, in particular the idea of a black box, well-defined inputs and outputs, interfaces. We talked about the idea that components should be designed to do just one thing and one thing well, and that they're meant to be reused by many other components that form part of a bigger solution. And just as no man can be an island, therefore neither can any component work on its own or solve a bigger problem on its own. In his book, The 7 Habits of Highly Effective People, author Stephen Covey talks about the maturity continuum, the move from dependence to interdependence. Sometimes I think Mr. Covey was a computer scientist at heart. Although I have no actual evidence to prove this, I particularly like his "you're the programmer" analogy to his first 2 habits. Components too have a very similar continuum of maturity. In their infancy, they tend to be very dependent. They were created for a specific purpose, perhaps a specific project to solve a particular problem. And at that level, the component was highly coupled to that end solution, and it wasn't very cohesive. But as time elapses, and we apply those architecture principles of what makes good components, they evolve and become independent, generic, adaptable to a wider variety of problems and situations, and they save us the time from having to recode, fix, or change the component. We simply consume it for our latest project. In fact, they become our personal go-to toolbox. Why reinvent the wheel? Today's presentation is about the 3rd phase in this maturity continuum, interdependence, to use Covey's example. It's not enough to have a database server that no application uses, or a web server that gives content to the user but never does anything else, or a travel management system in our example that can't talk to other hotels to make reservations or talk to other airlines to make flights. No, for something to be of true value, it needs to be lasting and consistent. It needs to recognize that by itself it can't solve all of the problems on its own, but it needs to work with others to fulfill a greater purpose. Because what can be said of humans also applies to the things that humans make. The key to this interdependence in our components relies in our ability to make long-lasting and consistent relationships. The ability to have great components relies in those relationships those components have with the other components to fulfill a greater vision. So today's session is going to talk about 2 specific topics: inter-process communication, which talks about how the relationships between different processes work together to allow those individual pieces to communicate one another back and forth. And a specific form of interprocess communication we're going to talk about is called the remote procedure call, which is the idea of calling something remotely on a distributed computing platform. So different machines are responsible for processing different parts, and they all come together to form a part of the greater whole. So just like in part 1, all of our examples today are going to be using C#, and all of the details of compiling them are going to require a C# compiler. So you'll need to learn C# if you don't already, and you'll need to have your environment set up in order to compile them. And if you want more information on how to set that up, you can refer to part 1, and I go through an example. We're going to build everything on the Windows operating system, and you don't need a fancy IDE like Visual Studio, but if you want to use that, that's fine. It'll work just great that way too. So as an example, let's pretend that we have in our travel management system a spot for making hotel reservations. So think about a system like Travelocity. So you go to the website, you log in with your account, and you say you want to book a hotel. And it's going to collect the details of where your stay is going to be, when you're going to check in, where you're going to check out. And at some point in that process, it has to send those reservation details over to some hotel. So let's pretend that it's the Hilton, and actually make the reservation at that hotel for you, and then come back and tell you whether or not your reservation was successful. So on the client side, we have the Travelocity server, and there's another hotel server sitting there, and it's basically taking those requests and actually making the reservation. So your interface is sort of this make reservation system. So one simple, but at the same time powerful method to solve this problem and communicate your details about your reservation is to use a batch job. So we could, for example, have a system that's sitting and waiting for a file to come in. And when that file comes in, our hotel server will read it, read the details of the reservation, store it in a reservation database, and then the reservation will be made and maybe return the room number that was assigned. So it's basically going to wait for this trigger. The file is going to exist. When the file exists, it's going to open it and process it. So let's look at an example. So let's take a look at some of this code from the architecture principles of building a good component. So the first one I mentioned was organization. So you can see that our main server is an object that we called hotel reservation server right here. And it's using a component within our travel management system that we called hotel reservation request right here. And that object comes from the travel management system up here. So it's going to be a separate DLL component that we're going to have linked just for dealing with hotel reservations. Now, just from looking at this, can you tell whether or not I did it from a top-down or a bottom-up approach? It might look like, from your point of view, that I did a top-down, where in actuality, I actually built it bottom-up. But because it's already done, it appears like top-down from your perspective. You can see that the input is not being validated as an example. We're just assuming that whatever's coming into the file is okay. We're not checking it in any way. So you could imagine there could be two different interfaces. So one interface could be the web, where a person goes in and types in their check-in and check-out information, and that changes to the server. But there could also be the clerk at the desk that somebody walks up to and wants to make a reservation, and he types it into a different system, not the web-based system, but maybe it's a old-fashioned green screen system, or maybe it's a forms-based system, but it needs to talk to the exact same interface. So this gives you the ability to do that. So as part of our organization structure, we have three different files. One is called reservation request. So that's going to be responsible for the core component of taking the details of the reservation and sending them over to the server. We'll have the reservation client. So it's going to be responsible for gathering the details when that check-in, when that check-out is. And then we have the server that's going to take that details that has been gathered, call the reservation request component, and actually process the reservation and then delete the file when we're done and store everything in the database. So we have a good example here of separation of concerns. Inside this object, which is specifically to deal with hotel reservations, we have process reservation, make reservation, get room number, and update database. So that shows a good example of cohesion. All of the things regarding reservation requests stay together. And we have a good example of organization. We've broken everything up into its own files. So our reservation server uses that travel management system component. So we can see travel management system. It is just a main loop that's going to constantly look over and over and over again for this file called resreq.txt. If it finds it, it's going to call that object process reservation, read that file, delete that file, wait about 2.5 seconds, and then continue through looking for that file and over and over and over again. So that shows a good example of separation of concerns and organization. Now, in terms of reusability, because we separated our server, which is basically making reservation requests, we could potentially have different systems calling the hotel reservation request. So there could be multiple hotels, all of which have different ways of making reservation requests, and because we've put it together the way that we did, all of those different hotels could potentially use that same shared object to handle their reservations. Or from an interface perspective, there could be a web interface for users that might be connecting with one version that's going to create that common reservation request, but then there could be another interface for, say, the front desk clerk. So when he goes to his system and he types in the details, it still has to create that same text file, but the server processes it regardless of where it comes from. Although the interface is quite generic, in this case it's just a line, a reservation line, it's still kind of tightly coupled in the sense that because we have the two DLLs coming together, both of them have to rely on the same language, in this case C# or at least .NET, in order to link the DLL to the main code. So there's a tight coupling there, and we'll see a little bit later how that could be loosened up, make it even a little bit better. Separation of concerns. So note that the process reservation component reads each file line by line, and it just calls that process reservation. It has clear boundaries. So if I want to compile each of these components, I'll first compile the reservation request, and I'm going to make it a library. Recall that's the file that contains the make request, the process request does all the work. And let's then compile the and if I run the server, all it's doing is it's sitting there in that directory looking for this resreq file, and when it finds it, it's going to process it. So that's all that is. It's just a batch example of interprocess communication that's using a file for the common interface between the system. And that's all it does. It's just sitting there. Now, it hasn't seen a file yet, so it's just going to sit there and run basically infinitely. So you could imagine that's a server sitting at the Central Hilton office, if you like. So let us then look at the client. So I'm going to open that up in a different window. Just to show you the code. The reservation client, its job is basically to get those details of the reservation. So when is your check-in, when is your checkout? It's going to read those from the console. And basically all it's going to do in its do reservation method is take those details and write them out to that resreq.txt interface that we define that the server will read. So let's note that right now there are no text files. The database reservations.text contains some sample ones that I did before. So let's run the client, reservation client. It's going to ask me for a check-in date, 2018, May 5th. And let's say I'm going to check out 506, 2018. And it's going to ask me for a name for my reservation, Jack Doe. Now watch. There's the server constantly waiting for that file. There's the client. It's going to create that file. So when I hit enter, the file got created. It found the file. It read the file. And now if I looked at the database again, you can see that it just changed it. And now it's added that new Jack Doe and assigned me room 1 on May 8th, 2018. So this is great if you have something that you can process once a day or you want to process on a regular basis. It's the batch method of inter-process communication. You basically have a batch job that's running every so often looking for a file. And if you take a moment and think in your organization, you probably have lots of processes that use this type of system. At one point, something comes together and a file gets produced. Some other process might run 10 minutes later that picks up that file, changes its data around, dumps it to another database or dumps it to another file or sends it to another application. So that's inter-process communication. Those two processes are interacting with one another, and the file and the contents of the file and the specifications that make that file up are both shared by both applications. They don't even have to be on the same machine. In my example here, my server and my client are running on the exact same machine, but this could have easily been a server running 100 miles away as long as they can share the same file. There are some limitations, of course. It's good for processing things at night, like for example at a bank. You might notice that when you make all your credit card transactions, they don't show up on your bill right away because there's a nightly job that picked all those transactions up and process them. It does require that both systems have a common file system, so that might not be practical in the case where I'm making hotel reservations at hotel chains all over the world. They're not all going to share the same file system, but it's very easy to implement. It only takes a few minutes to create something to watch for the file and to process the file, and then another interface that creates the file. It's not real time, so I didn't get feedback right away on whether or not the reservation was successful or failed. It might not happen till the next night. It might happen every couple of hours. So if you have a situation where you don't need real time, batch job can be a very useful, quick thing to implement for inter-process communication. So let's suppose we want to extend our simple reservation system to allow a user to make reservations at a wide variety of hotel chains. So for example, the Marriott or the Sheraton or the Delta or the Hilton. I'm sure you can think of websites out there like Travelocity or Expedia where you can basically look at different hotels, pick the ones that are cheapest in the spot that you're at, and make a reservation directly. But all these systems don't have a central reservation component that all companies use. In fact, many of those probably went to their own system, PHP. So how could we possibly get all of these companies to agree on a common interface? Heck, in some companies, you can't even get people in the same department to share data with one another, or even different development teams to work together without any kind of conflict. So how in the world are you going to get all of these groups to work together on a common interface? But let's take a minute. Let's imagine where each of these companies subcontracted different companies, different firms to build components for them. And all of those components followed the very same architecture principles of good design, good software engineering. Now building a common interface that allows things like Travelocity and Expedia, they become much simpler, much more of a reality. What was once a dream is now a very real technical probability. But the question then might become, why? Why would a hotel chain that would allow any external interfaces into its reservation system? Well, put simply, it's good for business. The Hilton, and probably others, hire a call center. They cost lots of money. They have staffs, hundreds of personnel to receive the requests. They type these into some proprietary reservation system that they paid lots of money to initially have and lots of money to ongoing support. Or they might need to build their own web platform, which allows self-serve customers to log in and book their own reservations. So even more money. Or instead, they could implement a common interface that allows other systems to connect to them and make reservations with their system. So that one has a lower initial cost and lower ongoing maintenance, and the other companies in the world can invest into having connected different hotels. Most likely, they do all of these things, because all of these things increase new avenues for people to invest into their system, for people to make reservations, to increase their throughput, their ability to turn their revenue around even faster. This isn't even true for just for-profit either. A nonprofit could benefit because these different integrations will lead to different cost savings and a more timely service and a smaller footprint and achieve the same benefits as would have for a for-profit business. Now, obviously, for security reasons, you won't just let anyone into this proprietary system to do whatever they please. And you don't just start opening up firewall ports directly into your proprietary reservation system. Instead, you need to build an interface that works on top of that and just exposes the details to the world at large in a safe and secure way. And this is where we get into the open-close principle, because you're not going to change your existing system. You're simply going to build an interface on top of it and expose just the details of that interface. Now, earlier, I made the wording that we're consuming the service. So why do we say that it's consuming? So if we think about eating food, when we eat food, we take a whole product, like a sandwich, and we chew it up, and we break it into smaller components. And our digestion process breaks it up either further into the chemical compounds that our body needs, like glucose, to give us the energy. So in our batch interprocess example, the batch is consuming the file. It's opening it, breaking it up into the series of lines, and then processing each line, using it to make a successful reservation for the user. As I've noted before, though, the batch job has some limitations. It's not as cohesive as it could be. For one thing, both systems, although they don't have to rely on the same language, do have to have some sort of shared file interface. So if you're a company and you want to provide the ability to go register with reservations in multiple different ways, it's unlikely that you're going to make your file system open to anybody who wants to consume your ability to make a reservation request so that anybody can just write files to your file system. So a solution to this problem is what's called the remote procedure call. So let's imagine that we have two systems. In one case, the travel management system, which is going to be collecting the details about your check-in and your check-out, and the server. So similar to the client and the server we had before with the batch, but now our interface, instead of being that file in that file format, is going to be a service called Make Reservation. So the client machine will call the Make Reservation service sitting on the server of, say, the Hilton or the server of the Marriott or whatever other hotel, and it will simply be the responsibility of the server to make the reservation and the client to collect the details and confirm that the reservation is successful. The hotel server is providing that Make Reservation service. The client is calling the Make Reservation service. It's consuming it. So we call that a remote procedure call. When a solution is working by calling multiple remote procedures across different machines, so our travel management system is going to be calling maybe a Make Reservation service that's used by the Hilton, or a Make Reservation service that's used by a Delta, or a Make Reservation even that's used by a car rental company. That's called distributed computing. So the solution in our organization has to contact multiple different machines. That's distributed computing, and sometimes it's shortened as DCOM. The other way to look at it, sort of the other side of the coin, is if you're the organization, let's say the Hilton, and you're offering a set of services, a make reservation service, a take payment service, a room availability service, then when your organization views your solution offerings as a set of services that can be consumed by other parties, whether it be inside your own company or outside your own company, we call that service-oriented architecture. So you have a service-oriented architecture when you're viewing all of your solutions holistically as a set of services that can be consumed by others. If you are the solution that is calling the other services, then that model is a distributed computing model. So really what I'm saying is service-oriented architecture and distributed computing are the exact same thing, just looked at from different perspectives, different sides of the coin. From the point of view of the organization offering multiple services, you're doing service-oriented architecture. From the point of view of the solution that is calling those multiple different services and consuming them, you're performing distributed computing. So let's just remind ourselves of what that original reservation request looked like. And there's the hotel reservation request. There's that method process reservation, which reads a file, so we don't really need that. There's the process make reservation, which takes in the reservation line in the database, actually looks up the available rooms. So again, we're making an interface into this method. So when people call it, they won't be calling this directly, they'll be calling our interface, and our interface will then call this to do the work. So this is an example of the open-close principle. I wanted to add a feature that allows my reservation request to be called by third parties, but they're not going to directly modify this class, they're not going to directly modify this object. So in this case, my interface has been extended by using the process of encapsulation. Another common way to do it is to use inheritance, but in this case I've encapsulated the reservation request object inside the reservation request interface as a method of just extending that one part to the third party without giving access to everything else. Now let's take a look at the client and the server. So a little different. Server version 2. So again, we have a main function. Now instead of our main function waiting for a file to appear and then processing that file, what it's going to do is it's going to open a port over the network on channel 8888. It's going to make that port available for a request of an external object. So you have to take in the type. So in this case, I created my interface called the hotel reservation interface. So I'm saying I'm going to register a type called the reservation request interface. And then I have to kind of give it a handle. How am I going to access it? So it's going to be, the handle is going to be called RESREQ. I could have called it whatever I want, but this is similar to the idea of a file name. My file name was called RESREQ.txt. I'm saying now what I'm passing back and forth is going to use this handle called RESREQ. And then I'm going to sit and I'm going to wait for incoming connections. That's what wait for single call does. And it's basically going to be stuck in a loop, waiting for different requests to come in to call this procedure remotely. Unless I push enter, in which case it's going to stop the program. Now, if we look at the client, we'll see that our client is similar to before in the sense that we have a get request details, which is going to ask us the check-in date and the checkout date. But what we've changed is our do reservation method now, instead of writing an RESREQ text, so instead of needing to have this shared directory, the shared spot, it's going to open up that port 8888 and it's going to send those request details over. So you can see here that we're going to call this get object return over this address, and the address that we're popping in is the TCP port 8888 on the local host, and then the actual channel, the actual handle that we're going to use, RESREQ, which is that same RESREQ that you've seen in the server. Now, this is using a process called .NET remoting to set up those TCP port channels and to communicate the information back and forth. .NET is doing a lot of the work for you in terms of creating the network sockets and doing all the listening and doing all the forking. So if you want to know the details of how .NET is doing that, then I would recommend that you view the Internet Programming 101, which explains how it's setting up a socket on both ends for listening to, how it's splitting that connection, and then how it's defining a protocol back and forth that will send the data back and forth over the network. This is doing it the exact same way, it's just in the .NET world, it's hiding all of those details. So it's actually compiling into a very similar system as to the web server that we wrote earlier in Internet Programming 101. So if you want to understand the details of how all that works, just go look at that video. Now, the first thing I want to do is I want to compile my interface. So my interface is going to be a new library, and we're going to call it reservation request interface.dll. And I'm going to statically bind the reservation request.cs, so our original reservation request. I'm going to statically bind that with the reservation request interface. So that's going to build a new DLL, reservation request interface DLL, that's going to take those two reservation requests, which is the original request that our batch job used, and it's going to apply an interface to it that is basically encapsulating that request into its own DLL. So now you'll see we'll have reservation request interface .dll. So that's our interface. Now, to get this to work with the server and the client, I have to compile it as I've done before, saying I want to use the reservation request interface and the reservation request server request req interface.dll uses reservation request. So that's going to build the server. And I'm going to do the exact same thing to build the client. Okay, so let's take a look, an example of this in action. So in our situation, in our hypothetical situation, we have two systems. One is going to be a hotel, let's call it the Hilton, and one is going to be our travel management system that allows people to make reservations at the Hilton. So in this box here, we're going to refer to this as the Hilton server. So just imagine this is somewhere over in Hilton's office. And just to show you, it has a database of people who have had registrations. So I'm going to start the server up on that system. Reservation server version 2. So that server has started. It's basically listening over port 8888 for different people to consume that service and say, okay, I want to make a reservation at that hotel. So it's just going to sit there continually waiting. Now let's imagine that this machine is our travel management system located somewhere completely different, and its job is to take the intake of the details of the reservation. So this could be a web browser, or it could be a green screen at a travel management office. Reservation client version 2. And as we've seen similar with the batch job, now it's doing the same sort of thing. It's asking me for a check-in date. It's going to ask me for a checkout date. And it's going to ask me for a name of the reservation under Lucas Styles. So now when I hit enter, it's going to consume that service over at the Hilton. It's going to contact them and say, hey, this person wants to make a reservation. And the reservation server receives it, makes its reservation. Just to prove that that worked, let's go back and look at the server and now look at the reservations.txt file. And we'll see there's where Lucas Stiles has been added, and he's been assigned room 1 in January of 2018. Actually, that's for an entire year. He stayed at the hotel from 28 anyway. You can see that there's no validation on dates. Okay, so once again, let's review. Components-based architecture is about solving problems. Think about using prefabricated software tools, and components are just tools. To make sure we build good tools, we follow a set of architecture principles. In other words, we learn from the mistakes of the past, mistakes that other people have made. They've built a set of common principles that we can follow. If we've applied all of these principles properly, what we've really done is developed a black box. So now others can consume our components. They're reusable by others, and they don't need to know any of the technical internal details of how it works. Think about a car. You can drive a car without needing to know how an engine works. You need to know you need to give it gas, but what the gas actually does, and what the spark plug actually does, and what the battery actually does, you don't need to know those details if you're driving the car. You do need to know them if you're maintaining the car. Components, just like humans, evolve over time. They go from a very dependent state for a very specific need. They grow to become independent and reusable on their own, and eventually they become part of the bigger picture of a common set of solutions used throughout an organization. Dependence, independence, interdependence. Components need to communicate well with one another. The ability of a component to work is dependent upon the strength of that relationship. That relationship is defined by a well-defined interface. How are we going to pass data back and forth from one component to another? When the method we're using to pass data back and forth, that shared data is across separate processes, even separate networks or separate machines, we call this inter-process communication. Specifically, if one component is calling another component remotely across a network in a distinct area, we call that using a remote procedure call. And at the examples we looked at today, we actually used what's called the .NET remoting framework because we're making remote procedure calls. Now, if you have a solution, and in our example we have our travel management system, and to deliver the travel management system, we are going to deliver it by calling multiple remote procedure calls, ones from different hotels all over the world, ones from different car rental systems all over the world, ones that might call different payment systems all over the world. So that then becomes called a distributed computing solution. We're solving it using DCOM. Now, the flip side of that is if you're in an organization and you're developing your solutions in a way to allow them to be consumable by others, and that's your service offering, we call this you have a service-oriented architecture. The slide is actually wrong there. It should say service-oriented architecture, SOA. Now, this isn't so much a principle as a rule of thumb that we use. There's a big difference between theory and practice when we talk about reusability. It's one thing to design a component to try to be reusable, to design it generic enough that it be called in different ways, to make sure that our interface is well defined but allows multiple different types of systems and multiple different types of languages to use it. That's sort of potential reusability. But as a rule of thumb, the real test that our components are reusable, we'll call it the rule of 3. A component has been successfully demonstrated as actually being reusable if it's been reused in at least 3 different solutions. So you can think about in your organization, is your component have at least 3 different solutions that are using that component successfully? And you can look at it in a bigger scale. You can say, okay, well, outside of my organization, are there other organizations that are calling my component? At least 3, there are 3 other organizations that are calling my component. And you could, so these different ways of saying, okay, well, I know that it's really getting a lot of use, it's really getting a lot of traction. If you could create a component and you say, well, yeah, that component's reusable, but nothing else ever actually calls it or uses it, it's not really reusable until it's had at least 3, and again, it's just a rule of thumb, to say, yeah, it's successfully now used as a reusable component. So of course the big question that I'm sure is on your mind right now, should I use component-based architecture in my organization? Is it a valuable thing to do? So to do this, we're going to walk through examples of two companies, Company A and Company B. So Company A has fully embraced shared components in their organization, and they develop their solutions as much as possible using shared components. And Company B, not quite so much. They kind of look at every project individually, and they kind of look at, how do I get the tools that work just for that project? And if I need to modify something, then I'm just going to go in and I'm going to modify an existing solution or switch it around to make a new solution. But they don't have those prepackaged, prefabricated toolboxes that they can use for all of their projects. So let's talk about the different types of scenarios. So in your organization, somebody comes to you and they say, we have a problem and we need to process orders and we're not properly collecting the orders. It takes too much time, there's too much duplication, and they need an automated solution to fix that. So if you're trying to solve that problem and you embrace components-based architecture, the very first thing you're going to do is you're going to look at your existing toolbox. You're going to look at your toolbox and you say, okay, what tools do I have in my toolbox that I can use to develop a solution to that problem? And you're going to be able to quickly figure out what tools, and maybe you need to add some more tools to your toolbox, or maybe you need to modify your solution, but you're going to be able to turn around a solution much faster. Organization B that doesn't quite have that toolbox of tools to look at is going to start rediscovering everything from scratch, reinventing the wheel. Well, how do I solve this problem? Well, yeah, I've solved it this way before. Maybe I open up the project that I did before and tweak it a little bit, but I got to change it here and here. And then how am I going to maintain that down the road? Because now I have two streams of similar type of things, but each of them actually works a little bit differently. Do I create different versions of each one and remember that this version is for this and this version is for that? So it's a little trickier. What if you've delivered a solution to the client and they ask you, okay, well, that's great, it works wonderful. Could we also ask for this feature? And then they say, how much time is that going to take? If you used a component-based system, you kind of have a toolbox again of tools that you can look at and say, well, what tools might solve that problem? But if you followed the principles of component-based architecture, you could say, well, can I extend some of my existing components to meet that particular requirement for that particular customer with confidence that it's not going to affect any of the other services that I've already provided? So you have an advantage there if you embrace components design versus if you don't follow components, and again, you're kind of reinventing the wheel. Let's think of another example. Suppose next year a new database system comes out. We'll call it DBMS2. And DBMS2 is 1,000,000 times faster than any database in existence today. It's just breaking edge, cutting edge technology, and everybody's jumping on the bandwagon saying we need to all move to this new system because it's so much more efficient. It's going to be so much faster for people. And let's even make it even better. Suppose it's free or it costs only $10, where the existing database server, maybe you're paying $1,200 a year to maintain. So you got a super cost savings, super efficiency. There's a huge push. Everybody wants to move to this database server. So in organization A, if you've embraced components, you've created a set of components to deal with the current database system you're on now, to deal with how you're going to open it, how you're going to read data from the database, how you're going to store data back into the database. There's basically an interface that your application is calling to do all of that work. And all of the applications in your organization call that common interface, that common tool that you have. So for you, upgrading to a new database isn't really that big of a deal. You need to now keep that same interface, but change the implementation details of your component to call the new database, to call its new methods, to do its new storage. So you get all those speed benefits in that one component. You're obviously going to do a lot of testing and make sure that everything works with the new database. But once you have it all set up, you've just changed one component, you've deployed it, and everything now uses it. You don't have to recompile all of your programs. If you're an organization B and you haven't embraced components architecture, you have a real problem on your hands because it might take you months, years even, to take all of your different applications and recompile every single one of them to work with the new database, and retest every single one of them to make sure that they all still work properly in the way that they're supposed to. You don't just have one central component that everything uses. You have to sort of figure out, okay, how do I make this one change? How do I make that one change? They each have to go through their own migration plan. I'll give you a second example. Suppose you're switching your authentication method. So you have a way of authenticating users to your application, and somebody discovers there's a huge security flaw. The way that that's working, it's possible to break into it and access it as a user without supplying the proper password. So when that's discovered, if every single one of your applications use the same component and that component has a flaw, you could go into that component, implement the fix for that flaw, redeploy that component to all of your applications, and suddenly they're all fixed. Now, what if you didn't embrace a component-based architecture? What if you did have that same authentication method copied into all of your code for all of your applications, but not built dynamically, not using those principles? Well, that means that now you have to go into each and every program and retype the fix over and over and over again, and rebuild them all again, and redeploy them all one by one. And then let's look at the example we did in the hotel. So you create a reservation system. Your reservation system at the Hilton is available to just your people, your managers, to put stuff in. And they say, okay, well, we want people online to be able to self-serve, to be able to register themselves, make reservations for themselves online on a web browser. So if you're an organization that embraced components forever, again, you're not too concerned, because all it really means is you need to build a new interface and expose that interface that calls the same old components that you've been using for 20 years, but you build a new interface on top of it. Now your end users access that interface, and that interface gives them what they need. But what if you were the organization that didn't embrace components? And now to you, the web is this big new thing, and everybody's moving towards the web. And how are you going to get to the web? Because all your system is based on green screens, is based on terminals. You know, even today, I made this video in 2017, and you can walk into organizations, let's say a store where you buy hardware, or a store where you maybe need to book reservations, and you look at their screen and you'll see that same old screen that's been around since 1982, and it's a green screen, and they're typing stuff in, and they have no web browsers. And other organizations, they're right onto the web browser, and they go into the web and they edit it, and it's like, well, why is it taking some people so long to adapt to technology that's now been around for more than 15, 20 years? Well, did they have a components-based mindset? Because if they didn't have a components-based mindset, that upgrade of that old system written on old mainframes may take 30 years, 40 years, where those who had always thought about components in the beginning, it might have only taken them a couple of months, or maybe a year or two. So components-based architecture allows you to do things much more rapidly. It allows you to solve problems by using an existing toolbox. And you're not forced to have to use the things in that toolbox, but when you can use those things, when you can take those advantages, you're going to deliver things to your customers faster. So that's why you should follow a component-based architecture approach. And when it comes time to go to service-oriented architecture and make yourself go to the web, again, to you, it's just an additional interface. You design that new interface and you expose it. Remember the whole idea that there's nothing new in computer science. Everything is based on the same old concepts. So a components-based architecture means that when the new thing comes out, when the next new thing comes out, you can make the minimal amount of change necessary and yet get all the advantages of whatever the new system comes out to provide. So now I'm going to ask the question back to you. Given the advantages of being organization A, an organization that embraces components-based architecture, an organization that quickly is able to adapt to change, take advantages of new changes, solve problems for the organization and problems for the client faster by having a rich toolbox of components to choose from, versus company B, which can't move as quickly, which has to come back and probably reinvent the wheel over and over again, which maybe has some idea of reusing certain parts of code, but is not necessarily following all the different principles of components and managing components. At the end of the day, take a deep breath and just ask yourself, which company do you want to work for?